Okay, now let us look at linear phase filters. Linear phase filters. Fair enough. Now, when designing filters, some aspects must be kept in mind. And number one of which is the filter, irrespective of IIR or FIR, must be causal. So, what is causality of a system? Let us refresh our memory. So, causality is nothing but when a system, so this is a system h of n, if x of n is our input and y of n is our output, a causal system will always have input, output that depends on the present value or the past value of the input or a combination of both. That is the definition of causality. So, for a causal system, output is dependent on the present or the past values of input. So, if y of n is equal to x of n plus x of n minus 1 plus x of n minus 2, this y of n, or rather the system h of n, will be causal in nature. Now say, let's consider another system x of n being the input and h of n being the system transfer function, and y of n is equal to x of n plus x of n plus 1 x of n plus 2. This system is said to be non-causal. This is because the output of the system depends on the present value of the system, and it also depends on the future value of the input of the system. So, whenever in a system the output starts to depend on the future values of the inputs, the system becomes non-causal. The same reference goes to the output as well. That means if a system depends on the present value or the past value of the input and output, the system will still be causal. If the system depends on the present values, not present values, the future values of the input and the output, the system will become non-causal. So this is just some recapitulation. So now let us consider a transfer function. So if a transfer function h of z is equal to b0 plus b1 z inverse, b2 z inverse 2, bm z inverse m. So looking at the transfer function, it is quite evident that the system or the filter over here is an FIR filter because there are no poles in the system. So this can be summarized B0 as summation n goes from 1 to capital M B of n Z inverse n. Now let us assume if n is less than 0, if n is less than 0, then h of z, which in our case is b naught plus b1, this will become, if n is less than 0, then this values will be negative, and negative when multiplied with a negative value will become positive. This becomes z plus 1, b2, this becomes z plus 2, and consequently it goes to bm z plus m. So this is yz over xz. So taking inverse z transform, we get y of n to be equal to b naught x of n plus b1, since there is z raised to the power of 1, so x n plus 1, b2 x of n plus 2, and this goes to bm x n plus m. So clearly the output over here, y of n, is dependent on the future values of the input. This will render this system to be non-causal. So in our case, the statement stands that FIR or IIR filter must always be causal. So a condition of causality must be derived from here. So if the system is to be causal, h of n should be equal to 0 for all n less than 0, because we have considered the condition n less than 0, and for that reason the system becomes non-causal. So system must be causal. Now causality is one of the most important feature, although it is taken for granted in designing filters. But this should not be the case, because in case of not filter, any types of system designing, we cannot predict what will be the future input of a system. We can predict the future output depending on the present input. That can be possible. But what we are providing to the system in the future, that cannot be simply derived or deducted in any fashion. So causality is an important aspect in case of filter design. Okay. Now let us go to the second condition, which is our topic of discussion over here, the linear phase relationship. So the linear phase relationship is another condition that is most sought after, and this can be easily implemented through the FIR filter. Why is that so? We will try and derive that through some argumentative processes. So before going into the arguments for why the linear phase relationship is most important, linear phase can occur in both FIR and IIR filters. But it must be mentioned that linear phase relationship or linear phase filters is more easier to be implemented through FIR filters rather than any causal IIR filters, although it is not impossible. Now, linear phase is very desirable because it can be implemented in speech processing and music processing. Now, sorry. Okay. Now, a filter having an impulse response h of n has a frequency response. H of n will have a frequency response h of omega or h of e to the j omega, where we can clearly write h of omega in the polar form as h of e to the j omega e to the power j angle of h of e raised to the j omega. So up until now, we just discussed about the magnitude responses. And this can be shown from the previous examples where we have plotted for the various poles and zero position. In the right hand side, we have taken the magnitude response. Say for example, if two poles occur over here, the magnitude response becomes something like this. This value was the magnitude response h of omega. So we are simply not bothered about the phase response. But now we shall shift the discussion to the phase response, as it is also quite important. So the magnitude response gives us only the weight of the frequency in the signal. So the magnitude response gives us the weight of the frequency. So from these plots over here, it is quite clear that the magnitude plot gives us at various points of omega the magnitude of the amplitude of the frequencies. But for a signal to be unique, the order in which this frequency appears is also very important, and this is quite evident. So let us look at an example. Say for in the case of an English language, we take three alphabets, say the three alphabets being O, G and D. These are identical or analogous to our frequencies. Now, in order to form a word, so if these are our frequencies, so if the alphabet are the frequency rather than the magnitudes, so the word that can be formed with these three alphabets be similar to our signal. Just compare it with an analogy, nothing more. So in order to form the word, we not only need the alphabet itself, but one thing we must also note that the order in which these alphabets occur. Say for instance, if this alphabet occur as in this sequence DOG, this is a English word dog. Now if it occurs in a different sequence, say God, the meaning completely changes. So evidently dog and God are not the same thing as a perspective of meaning. So using this analogy, we will try and define that the order in which the frequencies occur is very much important rather than the magnitude of the frequency as itself. And this order in which the frequencies occur is determined by the phase response of the frequencies. So it can be written, the phase response will have the timing information of the placement of frequencies. Fair enough. Now let us write the transfer function h of e raised to the j omega is equal to h of e to the j omega's magnitude times e to the power j theta of omega, where theta of omega is equal to the argument of h of e raised to the power of j omega. And this is because this can be written because theta omega and e raised to the j omega are both the functions of omega. So this equivalence is mathematically logical. Now suppose h of e raised to the j omega is equal to e to the power minus j omega n naught. So in this expression, e raised to j omega's magnitude will be equal to 1. Say there is an imaginary 1 over here. So the magnitude is 1 and the angle or the argument of h of e raised to j omega will be equal to minus omega n naught, which in our case is equal to theta omega. Now say if the impulse response or the impulse response or the time domain transfer function, both being the same thing, h of n is equal to delta of n minus n naught. That is, the transfer function is nothing but a shifted delta function or an impulse function. So what happens now if the frequency response of minus omega n naught means that a signal is delayed by n naught? So in other words, what the phase response says that, so what the phase response say is that depending on the frequency, a phase shift is created, which is proportional to n naught in the time domain, and all the frequencies are delayed by n naught, although the order of the frequency remains same. So here minus omega n naught simply dictates that the frequency, all of the frequencies of this transfer function are delayed by a value of n naught, and the order of the frequency will remain same. So minus omega n naught is our linear phase or linear function of frequency. So the prime utility of the linear phase frequency is that it simply delays the entire frequency set by a certain number of samples rather than changing its order. That is, if this is our frequency, what linear phase filter will do is simply delay the values of the frequency by a certain value n naught. Note that the order of the frequency will remain same. And this has been our task. If you refer back to the English language analogy, this signal and this signal are essentially the same signals, only there is a minor delay. That is the reason linear phase is desirable, because it keeps the order of the frequency intact. Now, linear phase's desirability can be much more efficiently defined by the terms of group delay. So, group delay. So, if e to the j angle of h, e raised to the j omega, can be written as e to the j theta omega, then the group delay defined by tau g of omega will be equal to minus d omega of theta omega. So the group delay tells us how many samples of frequency the signal has been delayed after passing through the transfer function or the system. So in our case, if theta omega is equal to minus omega n naught, then tau g will be equal to n naught. So this is a constant group delay, and if the group delay is constant, the filter or the system is said to be a linear phase system or a linear phase filter. And say theta omega equal to minus omega squared, then tau g of omega will be equal to 4 omega. So this is a variable. So this entire quantity does not become a constant, and hence if the phase response of the filter is given as some value like this over here, then the filter will be a non-linear phase filter. So this is the basic concept of the linear phase filters. Now in the next video, we shall study the FIR filter designing using frequency sampling method.